Welcome back. So far, I have discussed about the representation problem, realization problem, and after that, we have also understood that how to calculate the solution of the linear time invariant system, linear time varying system in some kind of closed form solution we are talking about. In this part of course, I am going to discuss about the one of the most important notion that is related to the input, output and state of the system, and that is called stability. And again, one can see that for particularly for the linear system, obviously some kind of extension is available for the nonlinear system also, but that is not as straightforward as the linear system. So due to that reason, we have two separate courses, one course about the linear system, another course about the nonlinear system. So whatever result that is available for linear system, people try to extend that result for nonlinear system, and most of time that is not possible. So in this course particularly, we are going to concern about the linear system. And in today's lecture, first I am going to discuss about the input output stability. So let us try to understand that what is meaning of input output stability, because we have already seen the definition of dynamical system. In definition of dynamical system, what we found that I have some physical system. If I give some input and if I know some internal variable that is called a state, then I am able to uniquely predict the output. So somehow I have relation between input and output, relation between input and state and output. So out of these relation, today I am going to see some characterization between input and output, and the goal of today's lecture is to introduce the first kind of stability, that is input output stability. So this lecture introduces a notion of stability, and basically that expresses how the magnitude of output relates to the magnitude of input in the absence of initial condition. It means that I am assuming that initially whatever system I have taken, that is in rest, means all initial condition or all state variable, value of state variable at t equal to 0, that is equal to 0. And after that I am going to give the bounded input to that particular linear system, and after that we are going to see their output. If you see the same kind of notion for nonlinear system, then people are talking about the ISS, input to state stability, input output stability, same kind of extension is available. So let us try to start the today's lecture. So first important concern is that why stability. So if system is not stable, then what happens? So we have to understand this. So if system is not stable, then system may burn out. And I have already told you that whenever we are formulating a large system, then there exist several subsystem, and all subsystem somehow interact in such a fashion such that if I will give some input, then I will able to generate unique output. So it might possible if system is not stable, it might possible that is disintegrate, integrate means breakdown happens, or sometimes saturate. Saturate means if you give any input, output remains the same. And after that, this kind of things happens for any small signal. So if system is stable, not stable, then you can apply any small signal, whatever phenomena, burnout phenomena, disintegrate phenomena or saturation phenomena might occur, and therefore an unstable system is useless in the practice. So one of the most important requirement whenever you are going to develop some system, you have to show either analytically or using some kind of mathematical guarantee. You have to show that your system is stable, means that is not going to burn out for the large class of signals. And due to that reason, stability is a basic requirement for all systems. And due to that reason, you might remember that when I have introduced the 6 different problems associated with system, I have given the much emphasis on the stability. Now, if you just consider the linear system, I have already told you that nonlinear system is a little bit complicated. So whatever result I am going to discuss in today's lecture, that is not straightforward applicable for nonlinear system. And I have already told you that linear system satisfy one of the beautiful property, that is linearity. It means that I can able to visualize the whole response in 2 basic part. First, what I will do, due to linearity property, I will put control equal to 0, and whatever output now that is going to reflect on the output channel, that is just due to the initial condition, and that is called zero input response. Similarly, now I am going to put all state variable, all physical variable equal to 0. Then whatever response at the output terminal, that is just due to the input, and that is called zero state response. So stability also can be analyzed using by decoupling in 2 different way. Zero state response, so zero state stability, and another stability that is related to zero input response. And if you see the stability that is related to zero state response, means when system is rest, that is called bounded input, bounded output. What does it mean? That if I have some linear system, if I apply some bounded input and suppose all initial condition equal to 0, means all state variable equal to 0, then my output is also bounded. Second form of stability, that is called marginal stability or asymptotic stability for the linear system, when we are putting input equal to 0. So what we are assuming that our system is just excited by the initial condition or initial condition of the state, and at that time we are talking about marginal stable or asymptotic stable. And we all know that whenever we are talking about zero input, it means that we are going to see some kind of behavior due to a state variable. A state variable will carry all kind of information, and that is internal variable. So due to that reason, second kind of stability, when input equal to 0, is also called internal stability. And whatever zero state response, means if my system is relaxed, then we are telling as a external stability. So different book are using different terminology, and you have to become familiar with both kind of terminology. And I have written as a note, the stability is defined for the zero state response and is applicable only if system is initially relaxed. That is from the definition. Now, before going to talk about the stability, because somehow now I have some kind of partial idea. Meaning of stability is that if my system is initially relaxed, then it is possible to show that if I apply the bounded input, then I will get bounded output. So first I have to define what is meaning of bounded input or bounded output. So basically in mathematics also, whenever we are telling that something is bounded, so then same definition is applicable. So basically this definition is brought from mathematics. So a input ut is said to be bounded if ut doesn't grow to positive or negative infinity. And equivalently, we are telling that there exists a constant, that constant is nothing but such that this condition will satisfy. So here I am assuming as a scalar, and due to that reason we are talking everything in terms of the absolute value. Suppose if ut is a vector, then at that time you have to calculate some notion, distance kind of notion, that is called nothing but norm. So in this course I will teach you, give you some brief idea of the norm, and in next semester there are some extensive course where I will tell you that how to define norm, basically why norm comes into picture, what is meaning of norm linear space. So these kind of things are very much required for the control engineers. So if ut is some kind of vector, at that time you have to take the norm, and again I am going to give guarantee that norm of ut is bounded by some constant then we are telling that that signal as a bounded signal, or here I am just talking about input, so that is called bounded input. Similar kind of things I can talk about bounded output. So suppose yt is output, then again yt is bounded by some ym, and that is less than infinity. So, and whenever we are talking about infinity, what does it mean? It means that we are telling that every time I am able to calculate the bound of some signal. That is the meaning. Infinity is very, very vague. So you have to understand the meaning of infinity very, very carefully. Now, let us come to the input-output stability of linear time invariant system. So in today's lecture, just I am going to talk about linear time invariant system, means and single input, single output, or multi-input, multi-output, both case I am going to cover. And in next lecture, I am going to talk about discrete time LTI system, and after that time varying system. So today's lecture is fully focused on linear time invariant system. So whatever result I am going to talk today, that is just applicable, we are assuming that is just applicable for LTI system. So now I am going to give one kind of definition, that is called bounded input, bounded stable. So what is meaning of bounded input, bounded output stable? That a system is said to be bounded input, bounded output stable if every bounded input excites a bounded output. So this is the definition, and with this definition I am going to talk about the next result. So now suppose if you have some LTI system, then how to check, how to drive some kind of mathematical relation such that you are able to understand that that particular LTI system is bounded input, bounded output stable. So suppose that if you have single input, single output linear time invariant system, and I am always assuming that my system is causal. Causal means that I am assuming that whatever input ut, that is not affected by the future output of the system. So under that assumption we are going to calculate the yt, and since system is in rest, so you know that if I know the impulse response of the system, so in form of convolution I can express the output yt. So this kind of result I have already derived in the previous lectures, please check it. So gt is nothing but the impulse response. And how to calculate impulse response? What you can do, at t equal to 0 you try to apply the impulse to the system, and whatever response that comes into picture, that is called basically impulse response. And due to convolution property of this integral, either you can write gt minus tau ut or g tau ut minus tau, both are the same. Now what we are telling, that my system, single input single output system, means yt belongs to R, some kind of real number, is bounded input bounded output stable if and only if. So here you can see that I am going to talk result on the both hand side. It means that if system is bounded input bounded output stable, then whatever impulse response, that is GT, is absolutely integrable in 0 to infinity. Why 0 to infinity? Because we are assuming that whatever engineering system that is only excited in the future time, and time we are not assuming negative. Similarly, if GT is absolutely integrable in 0 to infinity, then one can easily show that system is bounded input, bounded output stable, and due to that reason, in this theorem, I am going to use if and only if, means this is necessary and sufficient condition. Now let us try to see the proof, and proof is very easy. So first what we are going to show that if GT is absolutely integrable, then every bounded input excites a bounded output. It means that if I just check the impulse response of the system, so I have some system which is in rest, and after that I will calculate the impulse response of the system, and based on the impulse response, now I am able to give the guarantee that you can apply any bounded input, your output remains the bounded. So now my system is somehow stable in bounded input bounded output sense. So let us see the derivation. Because I am assuming that my signal, input signal, is bounded, due to that reason there exists some kind of so ut is bounded by some kind of and is less than infinity for all t greater than equal to 0. And now what we are going to do, because this is single input single output system, due to that reason yt belongs to r, so due to that reason I have taken absolute value here, and here I have g tau ut minus tau. And after that what I am going to do, I am going to put this integral inside absolute value inside this integral. And whenever, because here you can see that g tau may be positive negative, ut minus tau may be negative and positive, and due to that reason if that is negative and positive, so if we put integral inside, then this kind of sign comes into picture, and due to that reason this kind of means inequality comes into picture. Suppose both are positive, then inequality remains the same. Due to that reason equality sign is also there. And here you can see that I am assuming that control input is bounded for all t greater than equal to 0, and due to that reason, and I am not going to worry about the negative time, and due to that reason I am able to find this bond and because I am first assuming that GT is absolutely integrable. And what is meaning of GT is absolutely integrable? Means absolute integral of impulse response from 0 to infinity is some number, some constant number, and due to that reason this kind of response comes into picture. So you can see that here this will give some kind of picture also. What kind of picture? They are telling that if you apply some signal of highest magnitude then output is always lesser than and minus m is somehow the motivated from the impulse response of the system. So and for some particular system impulse response is always fixed. So if you know the impulse response, then always you are able to figure out about the output. So I have proof in one direction, means first I assume this, and after that I have proof in bounded input bounded output stability. Now I am going to prove in reverse direction, means first I am going to assume that if my system is bounded input bounded means stable, then GT is absolutely integrable. So this method of proof means, since I am going to use bounded input bounded output stability, and after that I am going to prove GT is absolutely integrable. At the same time, if you just put the not operator both side, means what I am going to prove now, that if GT is not absolutely integrable, then system is not bounded input bounded output stable. And if you know the proof technique, so one proof technique is called direct proof. Direct proof means I have started from something and I am going to conclude this. So whatever first part of proof, that is called direct proof. After that, another proof is called proof by contradiction. So we are started from somewhere, and after that in between we are going to create some kind of contradiction. Third method of proof is proof by counter example. So we are creating some kind of counter example. Fourth type is proof by mathematical induction. Another is counter positive. So in counter positive, what we are going to do, we are telling that suppose I have to prove something A implies B, then that is equally true that if we are able to prove that note B implies note A. So similar kind of things I am going to do here. So what I am going to do, I am going to prove that GT is not absolutely integrable, then system is not bounded input bounded stable. Because if I am going to start from bounded input bounded output stability, I am not going to able to figure out how to prove. Due to that reason, we are going to use this kind of method. We are going to add not operator both side. So if GT is not absolutely integrable, then for any arbitrary large n there exists T1 such that this kind of condition is satisfied. Because whenever we are talking about absolutely integrability, at that time this should be always less than infinity. So it might possible there exist arbitrary large n and maybe infinity also, and this kind of condition is satisfied. Now suppose I have some bounded input, so you can generate some kind of bounded input, and simplest bounded input I have generated like this, that if g tau is greater than equal to 0, at that time I am assuming that my input is +1, and g tau when less than 0, then at that moment my input is -1. So you can see that here I have selected bounded input. So now if you calculate yt1, then you can see that what happens, absolute value of ut1 minus tau is nothing but that is 1, and due to that reason this kind of things comes into picture, and basically I have to put absolute value here, then things become more proper. So I forget to put absolute value. So you can think like this, that absolute value of yt1, and after applying the absolute value, what happens, this relation comes into picture, and that is greater than equal to n, and it means that n may be any large number, so it might possible that is infinity also, and due to that reason we are telling that system is not bounded input bounded output stable. So in this way we have completed the proof of theorem. So this is one, and if and only if condition. So due to that reason you have to do proof in both sides. So I hope that using this example you are also able to understand that how to apply different methodology of proof. At least two methodology is used here. So before going to the next part of this lecture, I am going to give you one example. So let us come to the very simple example, and example here is I have taken that one kind of system which acts like some kind of unit delay system. It means that if you apply some delta t, then whatever output you are going to get, that is delta t minus 1. So impulse response of system, first I am going to calculate the impulse response. So how to calculate impulse response? So I have to fix ut, means I am assuming that I have ut as an input, so I have fixed ut equal to delta t, and if you apply delta t, then what happens, due to unit delay, this kind of things comes into picture. So I know the impulse response of the system, and once I know the impulse response of the system, I have already told you that next part is very easy. Now using convolution I can able to I can able to generalize the output for any input ut. So I have applied the convolution. I know the gt minus tau, so I have actually substituted t minus tau, and this is basically impulse signal. So property of impulse signal, now I can write like this. So basically what happens, yt is ut minus 1. It means that if I have system like unit delay system, so if I apply ut, then my output yt is nothing but ut minus 1. So that is my system. Now, so using convolution, I have defined the system, and here I am assuming that this system initially at rest. Then only I can tell that whatever system I have defined, that is that has this kind of relation. So that can, under that assumption, so all internal condition inside this unit delay, that is equal to 0. Now let us come to the second example. So in first example, you can see that I haven't used any kind of feedback. Now I am going to add one kind of feedback loop to the same system, and I am assuming that this is single input single output system, and this system actually consists one kind of multiplier, means some kind of gain, and after that one kind of unit delay. And here whatever feedback I am going to apply, that is nothing but positive feedback I am going to apply to the system, and RT is the reference signal. And this system is also called distributed feedback system, because whenever we have delay is involved at that time, in order to predict the future, whatever value of a state, so that I have to know from t equal to, because you can see that yt is ut minus 1. So in order to know the value at some particular time t, I have to know the all value. Suppose you have to know value at t equal to 0, so I have to know all value between -1 to 0, and that is infinite many information. Due to that reason, that is called distributed system. Now I have to first step is to calculate the impulse response. How to calculate impulse response of this system? Just you can apply rt equal to delta t and try to see the output. So you can see that this is unit delay. So at t, if I apply, then what happens? First yt is coming due to this, and after that this input is again whatever output, that is again going to become feedback, and due to that reason this kind of things comes into picture, because now t minus 2 comes into picture again by delay and a cube, and in this way I am going to calculate the impulse response of the above system with positive delay. And after that, if I know the impulse response, I have told you that it is pretty easy to see the output also. So by convolution integral, it is possible to calculate the output, and it is pretty easy to check that output is nothing but that is given like this. And one can also calculate the transfer function, that is the Laplace transform of inverse Laplace transform of the impulse response. And if this bi is less than 1, then at that time you can see that this is transfer function. And whenever you have distributed system, at that time you can see that this is not proper rational transfer function, this is some kind of irrational transfer function. Now my main aim to check bounded input bounded output stability. So how to check? So you have to just prove that whatever impulse response, that is absolute integrable. So you have to just check the absolute integrability of the impulse response, and here I have checked. And after doing this kind of integral, it is possible to show that, means this is very very easy to check that if mod a greater than equal to 1, then that is infinity. If mod a less than 1, then that is less than infinity. So it means that this system, whatever system I have developed here, that is bounded input bounded output stable, provided whatever gain I am going to select, that should be absolute value of that gain should be 1. So in this way, one can decide the gain of this particular multiplier block. And after that, now you can apply any bonded input. It is always possible to give that whatever output you are going to generate, that is always remains bonded. But if this A is greater than 1, then it is not possible to give guarantee that yt is bonded. Now let us again return back to the our lecture, because this is just one example where we have shown that how basically if some system is given, then how to talk about bonded input, bonded output stability. So this is the one of the way to talk about the bonded input, bonded output stability. Now if somehow you are able to understand that some system is bonded input, bonded output stable, then now you can see that, and obviously system is LTI, linear time invariant system, then you are again able to generate further more result. And what is another result? This result is suggesting that suppose your system impulse response GT, because if impulse response is a square means absolute integrable, then I can talk about bonded input, bonded output stability of whole system. Now suppose in place of impulse, just you can apply some kind of input ut, that is A. So I am going to apply some kind of a step input, and it is possible to show that in a steady state, because I am talking about t tending towards infinity. So I am not going to talk about transient state, transient response. I am going to talk about the steady state response. So if I know that LTI system is bonded input, bonded output stable, then at the one quickly it is possible to calculate the output of this system, and output is going to converge to this constant value where A is the input and G cap 0 is nothing but, you can see that G tau is the impulse response of the system, and this is the Laplace transform of the impulse response. And here, because I am assuming that ut is constant, due to that reason you have to put s equal to 0. So whatever value by taking s equal to 0, so that is integration of g tau d tau, so that value you have to substitute here. So that particular value gives you the output of the system. Similarly, now suppose you have some kind of bonded input, bonded output, linear time invariant system, you can apply sinusoidal signal to them. It is possible to show that output again remains sinusoidal. Another important quantity, you can see that whatever omega 0 and t, so whatever frequency omega 0, that is going to remain the same. Just what happens, that phase is going to shift by some additional value, and magnitude is also scaled out. So what happens, if I have a stable bonded input, bonded output stable linear time invariant system, and if I apply some kind of sinusoidal signal, then whatever output, that is again remains sinusoidal, and frequency is also remains same. Just magnitude and phase is going to become altered. Similarly, if you apply cosine signal, same kind of result comes into picture. Even if you can apply some kind of complex exponential, same kind of result comes into picture. And if you remember the lecture of the basic circuit theory at that time, because we are taking RLC network, that is linear network, and if I apply sinusoidal signal, then that will again generate some kind of sinusoidal signal only. So whenever we are talking about phasor, at that time we are using these kind of concepts. So now let us try to see the proof again. So how to prove it? Because I know that the impulse response of the system, and that is again impulse response is square integrable, means bonded input, bonded output stable. Now just I have to put in place of control, I have to put that constant amount A, and from here it is pretty easy to check that this particular quantity I can generate by putting s equal to 0. Due to that reason I have retained this. Similarly, if I apply ut equal to sine omega 0 t, so you can just replace t minus tau. After that, now sine omega t minus tau, so sine a minus b, you can apply that kind of formula, and omega 0 is some kind of constant, because here we are going to do integral with respect to d tau, and due to that reason this term comes into picture. Similarly, cosine term comes into picture, and after that, as because we are going to calculate the steady state response, due to that reason we are assuming that what is value when t is very large. So due to that reason I am putting t tending towards infinity, and if you do this, and in place of s if you put j omega, then what happens, that I can able to generate this kind of integral, and actually gt is the assumed to be implicitly to be real, and after that real part of this is given like this, imaginary part of this is given like this. So in this way I can separate the real part and imaginary part. So what is our main theme? Suppose you have this kind of signal, so I am going to express this kind of signal in terms of some kind of sinusoidal signal, and it is not difficult to check that. After doing the manipulation I will get magnitude and this kind of angle shift, and this is the proof. Similarly, we can do same kind of proof for the cosine signal. Now suppose if I have bonded means I have multi input multi output system. So till now we are assuming that whatever gt means impulse response, that is belongs to R, or yt belongs to R. Now I am going to take the multi input multi output case. At that time impulse response is in some kind of matrix form, and that is bonded input bonded output stable if and only if each entry. So now you have to check the impulse response matrix, and each you have to check that each entry should be a square integrable. Then only I can talk about that bonded input will give the bonded output, and proof is just the extension of single input single output case. Due to that reason I am not going to discuss that proof. So proof is very much straightforward. Now I am, before coming to this theorem, I am going to talk again one example, and here you can see that if you apply this theorem, means whatever theorem means, if system is bonded input bonded output stable, and if you apply the constant input or some sinusoidal input, then whatever output. Sometimes what happens, people are applying this theorem blindly. It means that they are not checking first that system is bonded input bonded stable, or in another way what we are telling, that impulse response of the system is square means absolute integrable. And if they apply the theorem blindly, then what happens, you can see here. So what we are going to do in order to demonstrate the blind application of theorem, I have taken this kind of impulse transfer function. I have just considered single input single output case, and here you can see that gt is not absolute integrable. It is pretty easy to check because this is exponential signal. So after some time it is going to blow up, and this system is not bonded input bonded output stable. And suppose without checking, if you try to apply this this theorem, then what happens, first you have to calculate the Laplace transform of this impulse response, that is 4s minus 2. So that will be defined always. After that, if you apply 1, then from the theorem it is possible to know, because we know that means if apply some signal ut, constant signal a, and this is the Laplace transform at 0. So Laplace transform of 0 at 4 s equal to 0, you have to put, so minus 2 multiplied by 1, so minus 2. But it is possible to show that since system is not bonded input bonded output stable, so even if you apply some kind of bonded input, your output become unbonded. So due to that reason, whenever you are applying theorem or whenever you are applying some kind of analysis, first please check that system is bounded input, bounded output stable or not. And similar kind of things you can also see if you apply some kind of sinusoidal signal sine 2t, then output and output, we have seen that output is nothing but that is given like this. This is the Laplace transform of the impulse response, and here from omega is 2, so due to that reason s equal to j omega I have substituted here, and after that we will formulate this. So finally it is possible to show that, means after applying the theorem it looks like this. But if you simulate this system, then again what happens, that your output become unbounded. So what kind of observation basically comes into picture? So suppose you have some kind of bounded input, bounded output system, then I can able to talk about frequency response. So magnitude response is given like this, phase response is given like this. But suppose if your system is not bounded input, bounded output stable, then at that time I cannot able to talk about frequency response, because these kind of things, because in circuit theory and lot of places in electrical engineering we are using this kind of concept, means or sometime in electronics engineering also we are using frequency response, means magnitude response, phase response. So before applying this you have to give guarantee that system should be bounded input, bounded output stable, means LTI system, linear time invariant system should be bounded input, bounded output stable. So, and due to that reason I have written this: if system is not bounded input, bounded output stable, its frequency response has no physical meaning. Now let us again back to the lecture, and now again I am going to talk about some more theorem, such that in a straightforward way you are able to check that some system is bounded input and bounded output stable or not. So what is two statement? We are telling that in this theorem two statements are equivalent. The continuous linear time invariant system is uniformly bounded input, bounded output stable, and every pole of every entry of transfer function has the strictly negative part. So if we see the transfer function, it means that in case of multi-input, multi-output system, I have some kind of transfer function, transfer matrix. So I have to see each entry of transfer matrix and all pole means whatever denominator polynomial. So root of denominator polynomial is, if that is strictly negative, then I can tell that system is bounded input, bounded output stable. So if system is bounded input, bounded output stable, then I can able to talk about this. And I am going to also talk about some kind of exception. So let us first try to see the proof of this particular whatever theorem I have proposed. Whenever you are proposing some kind of theorem, you have to give the proof. So proof is pretty simple. So I have taken linear time invariant system, and I have to calculate the transfer function. So transfer function is CSI minus 1b and plus d. So actually d is some kind of constant, so either you can add d here or not add. Then what happens, that because we have to just check the denominator polynomial, so d is irrelevant. So due to that reason we have to just check check the every entry of this particular matrix only. Now suppose that if that is a strictly proper rational transfer function that is given like this, and if in order to see the response, because this should be this whatever g means gij, that is the impulse transfer matrix. So if that is in time domain, then easily I can talk by absolute integrability of that function, and due to that reason I am going to take the inverse Laplace transform, and you all know that how to take impulse response transfer whenever we have this kind of things. And after that, if you take impulse response Laplace transform, then you are able to get this kind of relation. So you can see here that if some system, means this is a square integrable provided this lambda 1, lambda 2, lambda all the lambda value that should be strictly negative. and due to that reason that kind of condition comes into picture. Now what we are telling that if all Gij, all the poles lambda I have a strictly negative real part, then Gij converges to the zero exponentially fast and system is bounded input bounded output stable. It means that whatever equation 7, that is square integrable, and if one of the entry of pole with a zero or positive real part, then Gij does not converge to zero and system is not bounded input bounded output stable. And it is very clear from here, because if you if that is not positive, then what happens, that is not square integrable. so and I have already told you that either you can add d or not add d, that doesn't means affect our analysis. So now one more important thing you can see here, whenever we are talking about bonded input bonded output stability, at that time we are not going to see the basically again suppose u equal to 0, and at u equal to 0 I have some again, if you take the Laplace transform, at that time what happens, that means eigenvalue of this matrix comes into picture. So it is possible to show that even if eigenvalue of A is negative, then also system is bonded input bonded output stability. It means that bonded input bonded output stability does not say anything about zero input response. That is the meaning. And why this kind of things comes into picture, because I have to just check the square integrability of this particular GS cap. And what is GS cap? That impulse response matrix. So it might possible during this kind of calculation some of eigenvalue which has positive part, that might be cancelled. And for that what happens, we have generated one example. So let us first see some discussion, that if every eigenvalue of A has a negative real part, then every pole, means because pole is basically created from this A, because you can see that Si minus A. So and determinant of Si minus A, that is going to create the pole, and if that is negative, then every pole has a negative real part. So from previous theorem I can tell that system, this kind of system x dot equal to Ax plus But is bonded input bonded output stable. It means that by just seeing the eigenvalue of A, I can talk about the bonded input bonded output stability. Now but whenever we are talking about bonded output bonded input bonded output stability, we are talking about impulse response. So suppose if we calculate impulse response, during this calculation it might possible some kind of eigenvalue with positive real part might get cancelled, and in that case it is possible to show that even if some of eigenvalue of A matrix is positive, still system is bonded input bonded output stable. And due to that reason I have created this example, x dot equal to xt 0.ut. So here you can see that if you put 0, it means that my system is x dot equal to xt, and what is A? So eigenvalue of A is 1, so obviously that is unstable. If you calculate g cap, that is 0.5, so that is a square integrable. And if that is means transfer function equal to 0.5, it means that system is bonded input bonded output stable. And due to that reason we are telling that bonded input bonded stability doesn't say anything about the zero input response. Again we will see one more example, that is again conveying the same fact. And here I have considered the second order system. So I have this kind of system here, x t belongs to R2, and I have basically one input. And I have this kind of system. So I am again assuming that I have single input single output system, and eigenvalue, if you see that one eigenvalue is -2, another is 3. So it might possible by seeing 3 one can think that this system is not bonded input bonded output stable, but actually this system is bonded input bonded output stable. Why? First you can calculate the Si minus A, and after that you can calculate the impulse response. And if you see the impulse response, then what happens, this kind of expression comes into picture. And here s is -2, and due to that reason we are telling that means this particular function is again, and in terms of square integrability you can see that this is a square integrable, and due to that reason we are telling that this is bounded input bounded output stable. So now I am going to conclude the today's lecture. So what we have seen that stability is one of the most important requirement, because if somehow we are able to prove that whatever system I have developed, that is linear time invariant system, and if just by checking impulse response I can talk about the bounded input bounded output stable, and after that I will give it to user that now you can apply any kind of bounded input, then that will give you always bounded output. And due to that reason this is very important criteria. Now in next class I am going to talk about the again means how to extend the concept of bounded input bounded output for time varying system as well as discrete time system. So thank you very much.